Hi class, in this lecture we continue our study in chapter 3 by moving into section 3.3. And section 3.3 is about using systems to model data. So basically what we're going to do is using the methods that we learned for solving systems of equations in previous sections, we're going to apply them to situations where we have data that you can be modeled with some mathematical equation. And basically we're going to solve two equations like that and see where they're equal. Okay, so let's go back and look at example 1 of section 3.1. So what we did was we modeled the life expectancy in years of women, WT, and M of T men, of US women and men respectively, by these following systems. Okay, so the life expectancy of women was equal to 0.180T, where T is years since 1980, plus 77.49, and the life expectancy of men is equal to 0.197T plus 69.95. Okay. So what we want to do is we want to use a symbolic method to predict when life expectancy of men and women will be equal. Okay. So basically what we're saying here is we have this table, all right, and what we wanted to look at is we see that over time both women's life expectancy and men's life expectancy is increasing, but since the slope for men is much higher than it is for women, it's almost like 2 times as much almost, they should overtake it at some point. Okay, so when is that going to happen? When will life expectancy be equal for both women and men? All right, so we found this intersection point in the first section of 3.1 of the graphs of the two models that represent the event when life expectancy of men will be equal. But we can find this intersection point either by substitution or elimination. Substitution is actually the easiest. So to solve for this intersection point by substitution, we substitute, looking back, this 0.18T plus 77.49 in for L here for men, okay, because the life expectancies are given by this and this. So basically, if you're catching this, what we're doing is we're setting the two equations equal to each other. So to solve by substitution, we substitute the life expectancy for women for L in the equation for the life expectancy of men. And what we'll do is we'll solve for T. So when you set these two equations equal to each other, from here it's just solving a very simple linear equation. So I'm going to move this to one side, subtract this to the other side. And you'll see I get, when I subtract the terms with the t, I get minus 0.089t. When I subtract the constant terms, I get minus 7.74. And when I divide both sides by minus 0.089, the negative becomes positive, and you get t is roughly equal to 84.72. All right, so now what we do is we substitute this in for t in any equation. It doesn't matter which one, okay? So when I substitute, I pick the life expectancy of women and I substitute this in, I get roughly 86.64. All right, so here's what happens. So what we're saying here is the approximate solution to this system is the point 84.72, comma 86.64. All right, this is the time. So this is years since 1980. So this is roughly 85 years since 1980. And we're saying that in 85 years since 1980, excuse me, the life expectancy of both men and women will be 86.64. All right, so this is the same result we found in example 1 of section 3.1. And so according to the models, life expectancy of both men and women will be about 86.6 years in that year 2065. So all we really did here, remember, is we just set both equations equal to each other. All right, let's do one more. In 2017, a 2016 GMC Acadia cost about $33,763, and a 2016 Acura MDX cost about $43,868. Okay, now we're going to talk about how much they depreciate in value. So the Acadia depreciates by about $3,738 per year, and the MDX depreciates by about $5,275 per year. Okay. When will these cars, right? When will these 2016 cars have the same value? So notice that the MDX costs more but depreciates by more. The Acadia costs less but depreciates by less. All right, so what we're going to do is we're going to let some value V equal A of T be the value in dollars of the 2016 Acadia, and V equal some M of T be the value in dollars of a 2016 MDX. And this is going to be both at T years since 1980. or since 2017. Okay, so because the 2016 Acadia's value decreases by a constant $3,738 each year, the function A is linear because it has that constant decrease, and the slope of the graph is minus 3,738. The v-intercept obviously is 0 because that's years since 2017. 33,763, that's what the car is worth at t is equal to 0. So an equation here, the value of the Acadia, is equal to minus 3,738t. Okay, so that's years since 2017. So that's how much it's going down, plus how much it cost initially, the starting value. So you can work the similar equations for the function m. So this is for the mdx, and it's the starting value minus how much it depreciates per year times years since 2017, because that's what the year we started at. So what we're going to do if we want to find out when these cars will be equal is we just set the two equations equal to it. We take the first equation here and set it equal to the second equation here. So when you do that, you get the following. So the two equations are equal to each other. Now all you have to do is solve for t. So again, add over this value, subtract over this value. So minus 3,738t plus 5,275t is equal to 43,868 minus 33,763, or just this. And when you divide, you get roughly t is equal to 6.75. So that's approximately 7 years. So we conclude that the cars will have the same value in approximately 7 years. So to find out what that common value will be, just take this 6.57 and plug it into either equation. It doesn't matter which one. And what we're saying here is, look, after roughly 7 years, almost 7 years, the cars will be the same value, and they'll be worth $9,204 each. All right, you can do this by verifying it in your graphing calculator using that intersection option. And you can see here that you get roughly the same values here. All right, your homework will follow much like this.